Hi everyone, my name is Warner Berry from Berry Science Lab, and welcome back to quantum mechanics. Today, we're finishing what we started last time. We're going to be finding the eigenfunctions of angular momentum. Now, to recap on where we left off last time we talked about the eigenstates, which include both the eigenfunctions and the eigenvalues. Then we focused on finding specifically the eigenvalues while avoiding the eigenfunctions because they're very difficult to calculate. And we eventually figured out that they would always be m multiplied by h bar over 2 for some integer n, which means that the coefficient in front of h bar was always either an integer or a half integer. So that's good. We know what all of the eigenvalues are. But now, let's get to the more important half. How do we find the eigenfunctions? Well, as we sort of talked about last time, the beginning is about expanding into the great terrible world of spherical coordinates. How do we do that? Well, recall that L is equal to P cross R. In P, the way we define it in quantum mechanics, is just IH bar multiplied by nabla. So this is essentially nabla cross R. Now expanding nabla in spherical coordinates gives us IH bar multiplied by R hat over R, R hat cross R partial R plus R theta hat cross R divided by R. I should probably make it clear that this is the vector partial theta plus, so this is going to be R sine theta, theta cross, phi cross R, partial phi. Now this is pretty simple at first, because the cross product of a vector with itself is 0. So you can take this, rewrite it as R hat with the R scalar outside, and bada bing bada boom, this goes to 0. Simple enough. In the same exact way, this goes to phi hat, and this goes to minus theta hat because of the way spherical coordinates basis vectors work. Next, what happens when we simplify this?
I killed the fly.
Okay. I didn't even know that one was there. Sorry. This is not theta hat yet because, this is R over R. This is R hat. And theta hat cross R hat is phi hat. Same thing with this being equal to R hat. So phi hat cross R hat is minus theta hat. So we get partial R, well, that doesn't exist anymore since this is 0. Phi hat partial theta minus theta hat cosecant theta partial phi. Now we find it adequate to convert all the way back to spherical coordinates, which is, Cartesian coordinates, which is fairly simple. Phi hat just becomes, I think, sine theta, sine phi cosine phi 0 partial theta. Yeah, that's correct. Sorry, these should be minus signs. And cotan cosine to sine. And so we have over here cotan theta cosine theta cotan theta sine theta last component, it's just -1, multiplied by partial phi. Just to stop and make sure everything's correct, minus cotan, yeah, okay. Oh no, phi. Alright, so this is the equation we're working with now. And this is important because we actually need to separate it into angular momentum's Cartesian components, Lx, Ly, and Lz, so we can get back to doing the same things we were doing before. So Lx is going to be, just following all of the coordinates, sorry, this should be a comma, this should be a minus sign, minus IH bar sine phi minus, partial theta minus IH bar cotan theta cosine phi partial phi. Then for Ly instead, you have minus IH bar cosine phi partial theta minus IH bar cotan theta sine phi partial phi. And the z component is just IH bar partial phi. So as you can see, one of these is clearly simpler than the others. Great. We've achieved these. Obviously, that doesn't mean our journey is complete. It is actually nowhere close. It is just beginning. Now, we are going to define L plus and L minus. Remember, L plus is Lx plus ILy. And so, what does that become here? Well, this is, oh boy. Factoring out the minus IH bar, you get inside sine phi partial theta plus I cosine phi partial theta. As you can see, these are actually in the wrong order. That's important. Then, minus, no, not minus IH bar. So we have this and that counted in, plus cotan theta cosine phi partial phi, plus I cotan theta sine phi theta partial, partial phi. So here we go. This is L plus. And with a little bit of simplification, we see, what is this? Well, this is minus IH bar, and this can be simplified as what? Well, it's always cosine theta plus, cosine phi plus I sine phi. We always know that as e to the I phi. And of course, we actually see that going on here. This is e to the I phi cotan theta partial phi are working over there. But what do we do about this part? Because it's offset. Well, if we multiply this by I once, we get I cosine theta minus sine phi, which is clearly not working. So it's not going to be I e to the anything. Instead, this is going to have to take place as a phase shift, because of course cosine phi is equal to sine of phi minus pi over 2, and the same thing works in the reverse. So this can essentially be abbreviated as minus IH bar multiplied by e to the I phi plus pi over 2 partial theta plus cotan theta e to the I phi multiplied by partial phi. make sure everything's correct. Yep. So, this all gets simplified down to, why does it say Lx plus minus Ly in my notes? It should be Lx plus minus I Ly. I'm not sure why it says that. So this condenses down to minus h bar e to the minus I phi multiplied by, on the inside, partial theta minus I cotan theta partial phi. And if you want to add the minus side, then this is going to switch sides, and this is going to switch sides. Alright. So now, we know what L plus and L minus look like. Well, we can't erase that. Next question, how do we actually solve for the eigenfunction? Well, what are the eigenfunctions again? They're the functions that solve LZF is equal to lambda f. In this case, we already know lambda is equal to m over 2 h bar f. Now, we need to figure out what LZ is actually doing out there. Well, LZ is just IH bar partial phi. So, the h bars cancel out, and you get this very romantic proposition, that partial phi f is just equal to minus im over 2. Let's just write it as minus im for clarity, f. And what does that tell us? Well, f clearly has to have a phi component that's only e to the minus im phi. Everything else has to be in some sort of theta component. So what is the theta component? Well, we can't know anything else about it by just examining this formula. We're going to have to examine the other formula. Lx squared plus Ly squared plus Lz squared f is equal to lambda f. Now, of course, if we had to plug in these definitions in order to write this thing out in full, we'd all have to jump out of the window first. So instead, what we're going to do is abbreviate this using what we know. L plus times L minus is equal to Lx squared plus Ly squared, since these two are complex conjugates of one another. So, what we can know is that L squared at the end of the day can be written as L plus L minus plus Lz squared, essentially. It's pretty much that simple. Sure. Oh, it's a little bit more complicated than that, sorry. So, since these two don't exactly cleanly commute, Lx plus ILy times Lx minus ILy aren't as clean as you would expect them to be, because these are operators, not scalars. Which means that this is actually more like Lx squared plus Ly squared plus h bar Lz. Which means you have to add this guy to compensate for it. And there we go. This is L squared. That's at least a little bit more manageable than whatever that is down below. So we're going to forget both our definitions of Lx and Ly. They are now useless. Lz is still going to have to stay with us, even though it's relatively short, so I can probably write it. And now we're going to have to write this thing out. So L squared f is equal to m h bar f. Alright, now we write this out. How bad can it be? Very bad. Okay. plus LZ squared F minus H bar LZ F is equal to M H bar F. Okay, we're a little bit cooked. Let me just make sure this is correct. Okay. Yeah, obviously. Okay. So, when we write this out, what does it give us? Well, we get L plus L minus, which becomes what? H bar E. Well, there's going to be a minus H bar squared out in the back over here. E to the minus I phi multiplied by partial theta minus, let me just check which order they're in, plus I cotangent theta partial phi e to the I phi partial theta minus I cotangent theta partial phi. Now the dangerous thing is, it's very tempting to cancel these two out, but this right here is an operator that acts on e to the I phi. You can't drag it out that easy because this thing is still acting on it. But hold up, wait a moment. This is just the f term, the first term. Then you'll also have the LZ squared terms. What does that become? Well, LZ was IH bar partial phi, which means squaring that should give us minus H bar squared partial phi squared of F. That's LZ squared. Now you have this part. Well, that is actually pretty simple. It's just IH bar squared, sorry, since there's an H bar here, partial phi of F. And that all is equal to H bar squared multiplied by LL plus 1 F. Sorry, there's simply an M over here. So right now, this looks unsolvable because it is. What we're going to do is desperately try to reduce it to something we know. We didn't get this far in quantum mechanics for nothing to yield from this equation, right? So we attempt to go on and solve it. First thing to do, cancel out the H bar squared, because it's already getting annoying. So you get H bar squared here, H bar squared there, H bar squared everywhere. Second thing to do, we already know F is a mix of e to the minus im phi and another mystery function that we have to unbox. What happens when we plug it in? So we get e to the minus I phi partial theta I cotangent theta partial phi multiplied by e to the I phi. No, we still can't cancel it out. What's in here? Partial theta f, which means we're going to get big theta prime e to the minus I m phi. And then, over here, we have minus I cotangent theta partial phi f, which means the I comes down, or rather the minus I comes down, and minus I squared is minus I cubed, yeah, it's I to the 6, which is minus 1. So this becomes minus cotangent theta of theta e to the minus im theta. So everything in the parentheses is now covered. Now you have the outside, which is just this. When you take the derivative twice, then the im comes out of here twice and gives you minus I squared, of course, minus I squared is just plus 1 times m squared. What is this guy about? Oh, well, actually, this doesn't get the derivative taken. M squared e to the minus I theta. Okay, things are looking so far so good. At least as good as this monstrosity can get. Then you get minus I times minus I is minus 1. You get e to the minus I m phi. Then you get a theta over here. And, I mean, that's pretty much it. Finally, oh, sorry, there should be an extra m here, since you're taking the derivative of this via the chain rule. And of course, this is all equal to m times L plus 1 multiplied by f, which we all know is, oh, why did I put m here? M is equal to L times L plus 1. I'm a little bit dumb. So, we get L times L plus 1 e to the minus I m phi theta. Now we can't actually cancel anything out here. Not yet. We have to wait. Because it's very tempting to factor everything out and just go for the kill. But as you can see, these guys are still stuck in purgatory. All we can do is put this guy into these guys. Maybe that will help some. And so, we distribute the guys from up there. And what do we get? Well, we get e to the minus I phi partial theta plus I cotangent theta partial phi. What happens when you distribute this? Theta prime e to the minus I m minus 1 of phi minus cotangent theta big theta e to the minus I m minus 1 phi plus m squared e to the minus I m phi theta minus m e to the minus I m phi theta is equal to L times L plus 1 e to the minus I m phi theta. Now we distribute this derivative, because otherwise we'll never be able to do the satisfying cancellation of all the phi terms, and this won't become an ordinary differential. Oh, I'm spoiling myself, aren't I? So, what do we get? E to the minus I phi multiplied by... We'll leave the partial... No, we can't leave the partial. That'll just make things worse. So, we'll plug everything in at once. So, we take the theta derivative of this at first, which gives us theta double prime of this times e to the minus I and minus 1 phi. And then the product rule doesn't exist because when we take the derivative of this, it goes to 0. So then we get minus, that is going to be a mess, theta prime cotangent theta e to the minus I and minus 1 phi. Then you get well, then you have to take the derivative of this, which gives you plus theta times cosecant squared theta e to the minus I and minus 1 phi. Then you have to take the derivative with respect to partial phi, which means you get, well, this gets ignored, plus theta prime minus I times m minus 1 e to the minus I m minus 1 phi. And then you get, hold up. That gets multiplied by this, I cotangent theta, which means the minus I disappears, and a cotangent theta comes to fill its unhappy place. Okay, so that's one term. Then the other term is going to be, well, the same exact thing, basically. Minus I, hold up. Minus m minus 1 cotan theta e to the minus I m minus 1 phi theta. Yes, that's correct. Oh, and this would be cotangent squared. Plus, oh, and of course we have to distribute this back in. And what does that give us? This is minus I m phi. This is minus I m phi. This is minus I m phi. This is minus I, hopefully you can see where we're going with this. This is minus I m phi, once we put everything back in. Finally now, we get, well, what's left, sorry, this term, m squared e to the minus I m phi theta minus m e to the minus I m phi theta is equal to L times L plus 1 e to the minus I m phi theta. And now we can conduct the great cancellation. See this, that, there, this, that, thou, there, and this, 1, 2, 3, 4, 5, 6, 7, 8, all cancel out. And what do we get in the dust? As you can see, I left smudge marks all over the board, just trying to erase all of the things that we just cleared out. And so, let's erase what's now obsolete in order to make our new statements.
Isaac, baby, can you drink some water?
Yeah, I get it. I will. We get theta double prime minus theta prime cotan theta plus theta cosecant squared theta. Minus theta times m minus 1 cotan squared theta plus theta prime m minus 1 cotan theta, which means these two actually condense into plus theta prime m cotan theta. We already covered that. Plus m squared theta minus m theta is equal to L times L plus 1 theta. Now I want you to recognize this equation for a split second. Because if I multiply everything by sine squared theta, this precisely gives us the equation of the theta component of the spherical harmonic. Remember seeing these guys when we were solving the single-dimensional case? Oh, sorry. When we were solving the radial Schrodinger equation? Yeah, they're back. And, in fact, coincidentally, the phi component of these guys is exactly e to the minus I of phi. So, quite anticlimactically, the eigenfunctions were always just the spherical harmonics. Some of the most beautiful functions to ever exist. That's it for today. Tomorrow we'll be talking about spin, which is basically just this. We talked about how angular momentum has these discretized eigenvalues. Spin is just these eigenvalues, the intrinsic discretized angular momentum that any particle has. But of course, to explore it properly and more in depth, we'll need another full video. So until then, see you next time.